In the previous lesson, I showed you an algorithm for the knapsack problem, and the hope was that this algorithm is a p-TAS. And in this lesson, and the next ones, we're actually going to prove that this is indeed the case. Okay, so let's try to recall the definition of a p-TAS. So for a maximization problem, a p-TAS is an algorithm that takes as input the problem instance plus a parameter epsilon. And the value of the solution which is computed should be at least 1 minus epsilon times the value of an optimal solution. The second condition is that the running time of the algorithm should be polynomial in n, in the input size. For an f-p-TAS, a fully polynomial time approximation scheme, the running time should actually not only be polynomial in n, but also polynomial in 1 over epsilon. Okay, let's have a look at the algorithm that we developed in the previous lesson. So the algorithm has 3 parameters. The input, which is x, the set of items, and w, the total weight that we're allowed to select, and this parameter epsilon, which gives us the approximation ratio. Then, in the first step, we're going to replace all the values by value star. Okay, and we had a clever scheme by deriving a suitable delta and then replacing every value by the value divided by delta rounded up. That will give us a new subset x star, or actually it's the old subset x, but with the new values, value star. And for that subset, for that set x star, we're now going to call our dynamic programming algorithm, which gives an optimal solution for the case where all the item values are integers. And in x star, all the item values are integers. So that's what we do in step 2. And then after solving the problem on x star, we're simply going to say, okay, the subset of items that we compute is also the subset of items that we're going to report. So this is the algorithm. Now the goal of the lesson today is to prove that this is a p-TAS. To do that, we need to show 3 things. The first thing is that, well, the subset that we report, obviously its total weight should not be more than w. We should get a valid solution. The second thing is that the value of our solution should be good. And in particular for a p-TAS, it should be at least 1 minus epsilon times opt, right? Because we have a maximization problem here. And then the third thing is that the running time should be polynomial in the input size, in the number of items. So let's look at the first of these 3 things that we need to show. The total weight of the subset we select should be at most w. Well, that's actually pretty simple because we run, remember that we first change the values to value star, but we did not change the weights. So if we run our dynamic programming algorithm on x star, well, in x star, the items still have their original weight. So what we get is something that satisfies the weight condition. So indeed, the subset that we select has weight at most w. So this is okay. So now let's look at the second condition on the approximation ratio. So that's what we're going to do in this lesson. And then in the next one, we're going to look at the running time. Okay, so let's have a look. So now we want to analyze the approximation ratio of our algorithm. So let S be the subset of items that our algorithm computes. Right? And remember that S is an optimal subset for the set x star, which uses this value star instead of the real values. And let me denote by S opt the subset that gives an optimal solution for the real values. So this is the one that we would like to have, but we're going to have an approximation algorithm, so we're not likely to get this real S opt. But instead, we have our subset S. So what we want to show is that the real value of S is at least, well, we're going to give some kind of proof, and then it should boil down to that it's at least 1 minus epsilon times the value of the optimal solution. Or in other words, 1 minus epsilon times opt. Okay, so there are a few things we can use to prove this. The first is that, well, as I already noted before, the subset S that we compute actually gives an optimal solution for the value star. So in other words, the value star of S is at least the value star of any other subset whose total weight is at most W. In particular, it's at least the value star of S opt. The second thing we should use is the relation between value and value star. And remember that value star was defined as take the original values, divide by delta, and round up. Okay, so let's have a closer look at this, and in particular, let's have a look at delta. What was our delta? Well, delta was epsilon divided by n times a lower bound, and the lower bound we picked was simply the maximum value of any of the items. Okay, so let's have a closer look at the relation between value and value star, right? It's, well, value star is value divided by delta rounded up. So we can derive the following two inequalities. First of all, because value star is value divided by delta rounded up, it's at least value divided by delta. Okay, by rounding up, you only get something better. Sorry, something bigger. But also if you round up, of course, the value increases by at most 1. So the second inequality that we have is that value star of any of our xi's is at most value of xi divided by delta plus 1. Okay, and these two inequalities will be quite important in the proof that we're going to give. So, what can we say about the value, the real value of S, the subset we compute? Well, by definition, it's the sum over all items in S of the value of that item. And now what I want to do is I want to go from value to value star. Why? Because for value star, I know the relation between S and S opt. So first I want to go from value to value star. And to do that, I can use this inequality. So if I plug this into my formula, then what I get is that my value S is at least the sum over all items in S of delta times value star of xi plus 1. Okay, so now let's look a little bit more at this formula and let's simply rewrite. Okay, we can take the delta out of the sum and the minus 1 we can also take out of the sum, and then we get this. Okay, we've rewritten a little bit, and now let's look at it in a little bit more detail. So here what you see in yellow is the sum over all items in S of value star of that item. In other words, what you see is the value star of my subset S, and S was optimal for value star. So we had this inequality that said the value star of S is at least the value star of S opt. Okay, that explains how we can rewrite the first part of the formula we have now. For the second part, well, I can replace S, the number of items in my solution. Obviously, that's at most n, right? We can at most put all items in the solution. So S is at most n. And now if I use these two inequalities, then I can rewrite the formula, and this is what I get. Okay, so let's try to massage this a little bit more. So what we can do is if we use this inequality here, right, then we can go back from value star to value. So I'm going to rewrite this value star, use this inequality, and what I get is this. Okay, and now what you see here is that the sum over all items in S opt of the real value of that item. Okay, so this is the summary of what we've seen so far. Now we're almost there, just a few lines. So the first thing we're going to do is we're going to say, well, this part of the solution is simply the value of S opt by definition. Okay, so what we have is the value of S is at least the value of S opt minus n times delta. Okay, now let's simply plug in the definition of delta. So delta is epsilon divided by n times the lower bound. Okay, let's plug it in, and this is what we get. And now we know that the lower bound is at most opt, so I can plug it in, and this is what I get, and that's exactly what I want. The value of S is at least the value of S opt minus epsilon times opt, or in other words, 1 minus epsilon times opt. Okay, so we have proven what we want. We have proven that we get an approximation ratio of 1 minus epsilon. In the next lesson, we're now going to look at the final thing, which is that the running time of our algorithm is polynomial in n.